Okay, so let's welcome Professor. Thank you. So this is joint work with Spandan, who was a student at IIT Kanpur, CS student, like baptized into something non-CS, and now he's actually doing his PhD in a WH department. So let me begin. So here is a single snapshot of what convex optimization is. You have a function f, which is convex. You have a convex set over which you're trying to minimize. Very simple, everybody knows. So this is my small language model for convex optimization, which I use throughout the talk. Okay. So as you learned A for apple, B for ball, similarly F for convex. I'll also define what convex is. These are something which some of you might not know what is new strongly convex function is. Else, I think everybody knows, but else for the sake of completeness, so that everybody is not too hungry until 1 o'clock. Make sure people are engaged. So what is convex? Something in math, much easier in picture, that you draw a chord, it always lies above the function. It's the easiest way to remember what a convex function is. This is the mathematical way. There are so many equivalent definitions, but this is the simplest way to remember what a convex is. What is strongly convex? So it has the convex part plus an additional part which makes it even more curved. So again, in pictures, think of the function being mu strongly convex, it should be completely above a function which is mu times x square, more curved than that. And what is L smooth? Just the gradients are L ratios. That's it. This is in math, easy to remember in English. So this is more or less all the language I use today. I'll add D for dog, and that will be it for us. So what is onlineness in the convex optimization work? That's the most interesting part. So what is going to happen is sign will be slotted and we'll be interested in looking at total capital T time slots. At the start of slot 1, you'll be asked to produce an action without knowing what you're doing essentially. And once you produce that action, your action will be evaluated at a function f1. All the functions I'll talk about today will be convex or strongly convex. So no non-convexity anywhere in the top. So first an action is chosen, then a loss function is produced on which it is evaluated. And this process continues until capital time, capital T. FTs are convex. And what is revealed essentially is at time, so suppose you're at time little t, you know the history or the gradient history. You don't know what function you're going to be evaluating. And that is all you have to figure out what function or what action you do. Appears nonsensical at this time, but it makes sense anyway. What is a benchmark? What are you benchmarking against? So this will be a static benchmark. So what the adversary or an optimal algorithm can do is look at all the FTs ahead of time, but produce a single action which minimizes the sum. So it's not allowed to change its actions across time. For an algorithm, I'm allowing myself that I can change the actions, but for the optimal algorithm, he's allowed to only choose one single action, which minimizes the sum of the. And now I can define a performance metric for my algorithm, which is what is defined as static regret. So R stands for regret, S stands for static. So this is the loss function or the loss you're going to incur by choosing your actions evaluated at FTs. This is the loss the OPT is going to incur. And you take the difference of it. And that's what is defined as regret over the worst case choice of FTs, which the adversary can choose. That's my goal. So again, as I said, this looks hopeless that you can do anything meaningful here. But surprisingly, a simple algorithm can actually achieve a regret, which is scaling only a square root of it. And the algorithm is very simple. All you do is you take one gradient descent step. So at time t, the true function is ft, which is hidden. You have no idea what that function is. But you can see all the functions in the past. In particular, you see the function in the last one. On that function, this is my previous action, a of t minus 1. I'm going to take a single gradient step on this function ft of t. And that's my new action. I've not accessed ft at all. All I'm doing is I'm just choosing one gradient step on the previous function. I'm also throwing away all the functions which I could have used, f1 through f of t minus 2. All I'm using is the most recent function you showed me. And on that function, I'm taking one gradient step. This is the actual formula for one gradient step. and the step size is chosen appropriately. So if you choose the step size to be 1 by square root little t, what you can show is that the regularity is at most square root. The proof is actually 2 lines. I had it, but I decided to skip it. Instead, I'll show you picture why this should actually be appealing or should make sense that something non-trivial can be done. So suppose all the odd functions are x square. So f1 is x square, f3 is x square, f5 is x square. I have no idea beforehand. It's just that I'm constructing an example. And all the even functions are just shifted by x minus 10 whole square. This is actually a really difficult example for any algorithm. So what's the single optimal action? It is just to play x star equal to 5. If I have to play a single action, that would be my optimal. I somehow want to converge to this. That's my real goal. I don't know what these functions are because I don't even know ahead of time these are identical or not. They are being revealed one at a time. So suppose you start at A1, I had no idea what that function was. It will be evaluated at this blue function. And now I take, for finding A2, I take one gradient step on this blue function. So I go to A2, then I take another gradient on the red function. I go even further away. But now imagine A3, this function extended upwards, and that's the gradient will pull you back. So this is how this algorithm is actually going to oscillate around x star. If you do a little bit more, this is what the curve will look like. So exactly this. So I've chosen starting point as -5. It goes to +12 for this choice of functions, and just essentially oscillates around this x star is equal to 5 and converges to that. That's what essentially happens. So this is more or less what online gradient descent is doing for this particular problem. So this is all classical work. This will.
Why would it convert? Oh, because your step size is also becoming
1 by square root. So that's what is very important, that the step size is 1 by square root. 1 by square root of capital T also works. But then it requires the knowledge of the horizon. So 1 by square root T is even better.
And the domain is so.
Domain, everything is bounded here. So the functions are bounded, the sets over which I'm optimizing is bounded, everything is bounded. All right, so what? So now we look at the fixed action. Now let's look at what happens if the actions are not fixed for the OPT. So let the OPT, so we're just making the benchmark stronger. OPT is allowed to choose whatever it wants to choose. In particular, to choose the local optimums. And then you can define the same thing. So there's no change with respect to the algorithm. The algorithm's loss is the same. All I'm now subtracting is some smaller quantities. And the subscript S has become D now. It was static, now it is dynamic. So this is called the dynamic regret in the OCO, the online convex world is called the dynamic regret. And turns out that the same algorithm so let me define what a path vector is here. So each function, every time a function is getting revealed, let's call its optimizer x1 star, x2 star, and so on. And let's look at the difference between consecutive minimizers and sum it up. This will be my final thing I'll count in my language. This is called what is called as path length. And this will somehow appear multiple times on the top. So this is something useful to learn. So what is path length? You look at the successive minimizers and take the difference between them and add it across all of them. That's what I'm path. So it turns out that if you look at the online gradient descent, even for the dynamic regret setting, it gives you order path length result, and that's more or less the best you can hope for. So compared to a square root t, now it has become problem specific. It wasn't problem specific before. In the static setting, it was square root t independent of the problem instance. Now it has become problem specific because of the dependence on path length. Path length is input specific. So just add path length to your ABCDs and hopefully I'll not use anything about it.
So let's make earlier static regret. Does the bigger notation also hide the?
There are gradients and there are boundedness. So the diameter also is hiding there. The maximum gradients are also. Yes. All right. So essentially, what you should ask is what's missing here. In any convex optimization class, first you do one constraint optimization. So that's what we essentially done. And the next step is to look at constraints. So I will not talk about constraints today, even though we have some essentially closed up an interesting open problem, and hopefully Abhishek will talk very soon about it once the paper gets accepted. I will talk about something simpler. In the setting I've described, there was no penalty for changing actions across time. You could arbitrarily change your actions and there was no penalty for it. But that is not something which is appreciated by engineering people. And why I will tell you is the following. So instead of just the cost being evaluated at your function, I will also additionally charge you if you move your actions across time. So this is the additional penalty I'm adding compared to just the loss function. And think of ATs. So think of a large server farm where action AT is nothing but the number of servers you're engaging for processing jobs at time. And it pains them to change the number of active servers across times. That's the simplest use case for thinking about the online convex optimization and switching. And that's where it actually started. Then it became more theoretical problem rather than an application problem. But that's where it all came from. Think of AT as a number of servers in a large server farm which are active at a particular time. And you don't want to change that number frequently. And that's why you start charging that about the farm. For the rest of the talk, you can just think of it as a daily problem. All I'm asking is, don't change your actions across time too much. What can you say for the same problem just by adding this additional thing? And instead of regret, now it's much more meaningful to talk about competitive ratio, which Amit yesterday described. So let me just recap that. So the numerator is the cost of an algorithm. It's a minimization problem. So that's why the cost of the algorithm goes in the numerator. OPT's cost is smaller than any algorithm's cost, or at most that. So this ratio is always at least as much as 1, and you want to look at the worst possible input, which will maximize this, and your objective is to figure out an algorithm which can minimize this whole one. That's what we are. All right, so first of all, you should ask the question, why square loss? Why not something else? So it's a nice and smooth function, differentiable. It helps in analysis, but it comes with a simple restriction that if you take FTs to be only convex and no extra assumptions you make on that, the competitive ratio of any algorithm is unbounded. So it gives you something, but takes away something very large from you. So square has lots of analytical advantage, but it removes the fact that we can work with FTs being convex. So it forces us to look at new strongly convex functions. That's the reason why we are able to talk only about new strongly convex functions. If you remove the square and put just the norm, there are certain advantages. The biggest being that now you can work with FTs convex, but there are certain problems with analysis. All right, so that's why we're going to assume for the rest of the talk that functions are new strongly convex. Just to recap, what that means is this function always lies above our quadratic functions with a scalar of particular. That's what it means. So what else? So typical assumptions made is what is called as the full information model. So what is so this is, I'm deviating now for just for the second, that earlier I said action is chosen before the function is reviewed. But for this problem, where there is an additional penalty on changing your decisions across time, typically a model which allows you to see FT before you take action AT is used. Because the problem is still non-trivial, just by the fact that you have this additional movement cost or the switching cost. Even if I show you FT before you take action AT, the problem still remains non-trivial. But the whole point of this talk is to actually go from this full information model back to the original model which I talked about, where action will be taken before you show me. That's the whole point of this. So, and the bigger goal is that whatever you can achieve in full information, can I achieve in limited?
What are you comparing the to?
Sorry?
What are you comparing it to? What is the optimal?
Optimal algorithm has access to all the errors.
I mean, but are you charging optimal algorithm FTXT star or also this displacement?
No, so it won't be XT star.
Oh, it's just fixed, sorry.
No, so OPT is also allowed to choose whatever actions it takes, which minimizes the overall cost. So OPT need not go to the local minimizer because the movement cost of the local minimizer should be very large. So it will balance out whatever. So we don't characterize OPT. All we will do is to learn more. So the whole idea of this work is essentially what all prior work assumed this full information model, that action is chosen after FT is reviewed. So AT is chosen after FT is reviewed. We want to go back to the original OCO model where AT is chosen before FT. And what can we say? Can I get everything I get here with this limited information? That's the whole purpose. Question? All right, so let's just let me give you a brief idea of what algorithms were in the full information model. This is obvious greedy algorithm. So you are at time step 80 minus 1. I show you FT because of the full information. I just go to XT star. That's one possible option. Just play greedy. Done. Because of this, the function cost will always be less than the function cost of OPT because OPT cannot do anything better just looking at the first. But your switching cost is now as good as the path length itself. And what ends up happening is difficult to it's not directly easy to compute or compare the switching cost of this algorithm versus the switching cost of OPT. Because switching cost of OPT could be something much smaller, which is trying to balance this out. Something surprising will come out in a slide. So just hold on to this algorithm, which is just plain greedy, chooses the action to be the local minimizer. So it's hiding the year, so it was interesting that algorithm. So this is, I think, 80, fold 18. This is where the first guarantee came out. And the algorithm was slightly different than greedy. What it did, pictorially is much easier to see. So you're at 80 minus 1. You are shown FT. What you do, you take a quadratic curve of slope beta. So beta times 80 minus 1 whole square. And look at the point where it cuts this function FT. So this is nothing but this curve is x minus 80 minus 1 whole square times beta. That's the curve. And look at the point where it cuts the function FT. That point will be chosen to be a next point.
And what if it does not cut?
What if it will cut? Why?
Because if 80 minus 1 is on the right hand side,
Then it will go this side. Because I have this curve is symmetric around 80 minus. So I'm just showing you one direction, even if it's on this side. Unless it is exactly on the XT star, it may not go. In which case I don't have to. Right. So that's the algorithm, what is called balanced descent. What is it doing? It's trying to balance the two costs. One is the function cost, other is the moment cost. It has balanced it out in some way. So now I just have to keep track of one of the costs because the other cost is automatically related. And that's what they did. So then they only started to look at the movement cost and control it. And what you end up getting is that the competitive ratio is getting as 1 by mu. And when mu is a strong convexity parameter.
So in one dimension, there is a unique point of intersection.
Yes.
In higher dimension, there are many points of intersection.
You can pick any one. As long as this relationship holds. It's actually defined slightly more complicated. You take level sets and then you do something. But in essence, this is what. So 1 by mu is important to remember. So the competitive ratio is 1 by mu for this algorithm, which is working with full information and doing balanced descent. This is again hiding the year. Later on, somebody showed that the greedy algorithm is actually not bad. It achieves the same performance as the balanced descent.
It's not possible for the entire FT function to lie within the whole of this beta.
Which function?
So when you're drawing this,
Yes.
I mean this when you're creating a goal,
Right.
it's not possible.
But then it will sit. So 80 minus 1 is already at the optimum.
It may not be the optimum, right? It might be within. I mean, there might be some translate that you still some room that you have.
So you can fix that. So if that happens, you are okay to just use
The whole
80 equal to 80 minus 1 itself.
Right. Oh, yeah.
That's what will happen. Because of the strong convexity, all those things are taken care of. Convex, you'll have trouble. So now somebody showed that even the greedy algorithm, which doesn't do any balance, nothing, just go purely to the local minima. Don't worry about anything else. That also has the same competitive ratio as the balance algorithm. And then came the final thing, which is the optimal result. Slightly modified the balance with a regularization step. I'm not going to show you what that regularizer is, but just add something here and then try to find the optimal point. And that showed that the competitive, and this also is tied, the optimal competitive ratio scales as 1 by square root. And this essentially settles the problem in the full information. That if you have access to FT before you choose 80, you can get a competitive ratio of 1 by square root. What we want to do is to do this in the limited, if possible to achieve it or figure out what is the best. The rest of the graph will go back to limited. But you could time to ask any question.
That depends on the domain.
beta can depend on L and mu. So L and mu are known ahead of time. The algorithm has access to L and mu. Mu is the strong convexity parameter and L is the smoothness.
Is there a master version?
No, as far as I know. Even we will use L and even the limited influence. Okay, so what's the goal? The goal is to achieve the same performance as a full information, but with a limited information setting. So, thing you can keep in mind is people did so NASA went there, now they did this. If you understand what it is. Okay. So now let's just very quickly look at the limitation of any algorithm with limited information. That each algorithm has to suffer some combination. It's not very different to what. So suppose the original point where both OPT and U start is 0. Now in the limited information, A1 is chosen before the function is shown. So let the functions for tau time 1 through tau, where tau is very large, be identical mu by 2x square. So you can argue that until time tau, the algorithm cannot move from its original position, because if it does, it will pay a non-zero cost, while OPT will just remain at 0, pay 0 cost, and terminate the input right here. So the input will not go even further up. So that competitive ratio will be arbitrarily large. So an algorithm cannot do that. So you stay put at essentially at 0 location until time a of tau. At time a tau plus 1, I change the function a little bit. I multiply it by the Lefschetz constant or the smoothness parameter and translate the optimizer by a unit amount. So now it is L by 2x minus whole square. Again, you can argue that algorithm, because it sees this function after it has chosen a tau plus 1, it cannot move again. So again, a tau plus 1 is 0, in which case the cost is at least L by 2 times 1 square, which is L by 2. So the cost of the algorithm, any algorithm you pick, unless it is ready to pay unboundedly large competitive ratio, has to be at least L by 2. So the cost of any algorithm. Now, what can OPT do? Knowing these functions ahead of time, it starts at 0 and moves to 1. It has to get to 1 because L can be arbitrarily large, but it moves very slowly. And in the process, this is tedious computation. You can show that for these functions, if you want to minimize the cost, going from 0 to 1 in tau plus 1 steps, you can get a cost which is at most square root here. This is slightly tedious. I'm not going to show you how to do it, but you can do it. So in the process, what have we shown? We've shown that the cost of the algorithm is at least L by square root. So L is the artifact of the limited information. The fact that you're one step behind the information which has been revealed to OPT, the L comes from there, and the square root mu is the same as before. Even in the full information model, every algorithm has to suffer the competitive ratio at least 1 by square root. L is just because of lack of. So the goal is to actually achieve this competitive ratio. 5 minutes. Oh, so here is the algorithm with limited information, just builds upon online gradient descent. So I'm at 80 minus 1. Now the new function is hidden, I don't get to see. Again, I'm only going to look at the most recent function that has been reviewed. And instead of taking one gradient step, I'm going to take capital K gradient steps, where K is some constant, which will depend on the smoothness parameter and the strong convexity. So all we're going to do is to take capital K steps, gradient steps, to essentially towards the optimizer of ft minus 1. I have no idea what ft is. And that will be my new action, which I'll play as 80 equal to 80 hat. Step size will be 1 by L, not anymore 1 by square root P, where L is the smoothness parameter. So I need to know, somebody asked, I need to know L, and I don't remember. I don't think we need to know mu as well, because to choose capital K, we'll take L and mu both. So one property which is very useful, let's just see why something goes wrong. So with full information, all the analysis which we have seen essentially involved a potential function. And the potential function was of the following type. For example, this paper, you take the action you are playing, you subtract out the action being played by OPT, which is unknown, and then you try to look at the drift of this potential function, which is nothing but this difference in consecutive time slots. And this is some trick where you can show that the difference has some relationship between the switching cost an algorithm is paying plus the switching cost the OPT is paying. and then you amortize it over the cost of the algorithm and the cost of the OPT. So the functional part is essentially this, that this particular potential function is very helpful for analyzing all these kind of problems. With limited information, that doesn't turn out to be the case. And one great advantage of this potential function approach is it avoids characterizing the OPT in any way. It doesn't say anything about the OPT. It doesn't even try to find a lower bound. In a very hidden way, you're able to characterize what OPT is and how far you are from OPT. That's the great advantage of the potential function. It turned out that with limited information, we could not work with it because the information the OPT has is one step ahead of us. So we went for a brute force approach. What was our approach? Just upper bounded the cost of the algorithm and lower bounded the cost of the OPT. So this is an easy step. It essentially follows similar to what I said about the gradient descent for the OCO problem. The difficult step, which was also missing from the literature for so many years, was how do you lower bound the cost of OPT? One expects the guessing is not that difficult. What should be the lower boundary? Proving it was hard. And the proof essentially involved 3 steps. You exploit the strong convexity in a very non-trivial way. You do some delicate analysis with that. And the final thing was this very helpful for Gershgorin's circle theorem, which gives you some control over eigenvalues of matrices. So I will just state that and stop for today. I don't know if every student knows here. I was aware of it, but I never applied it before this particular work, and it turned out to be extremely helpful. So in the process, you end up showing that the cost of OPT is path length. If you remember path length, it is a successive difference square times mu, where the strong convexity parameter, divided by mu plus 4. And the circle theorem just states the following. So look at a matrix, look at any particular row of the matrix. You essentially remove the diagonal element of that row. So look at the SI will be the sum of the ith row other than the element, diagonal element of that. So you remove the diagonal element and take the sum of the ith row. The ith disk corresponding to this ith row is nothing but all points there, which are at a distance of SI from the diagonal element. That's the disk definition. And now the result says that all the eigenvalues of this matrix M belong to the union of these n different disks. It's a very strong statement and was very helpful for the following reason. So now, if you remember the switching cost of this quadratic function, it can be written as a vector A1 through AT with the same vector as a transpose here, and with the matrix M, where matrix M has a very special structure. That's where everything essentially came. It's not what is called as what the matrix called as, it's not circular except for a few things. It's the first row and the last row are not circular, but rest of them are all circular. And this was very helpful. This circle theorem was very useful to characterize the eigenvalue. This was essentially the way we computed the lower bound. So let me stop and not give the rest of the details. And I'll just go to, I might have made it sound a little too easy. This point to a simple problem which remains open. So this was the final result. So let me just summarize what we got. So lower bound was a function of mu and the path length. The upper bound turned out to be L times the path length. If you take the ratio, we got L by mu. What we wanted was L by square root mu or 1 by square root mu. We could not get that. For most reasonable algorithms, we were able to show that this is the best you can get. But this bound remains a conjecture because it's not for all possible algorithms. But for most reasonable algorithms, we could show that. And let me just get this. Yeah, so this is the problem which remains open, where the functions are just convex and the switching cost is just linear or just this normal distance. And what you want to show is to achieve constant competitive ratio when the information is limited. When the information is full, a trivial algorithm gets you 3 competition. So that's simple as I would even ask in qualified. But when you go from full information to limited information, all bets are off because of this non-differentiability of this. Okay, let me stop and let you have your peaceful house. Thank you.
Can you take federal trail?
Can I state?
Yeah. S needs to be absolute.
I do that. So, some of absolute. Some of absolute.
So also, so the matrix showed is almost the fraction of the random of an straight line. So you should have the full spectrum. So but the circuit theorem is in that sense
Was sufficient.
is sufficient. But like then for that, like,
Yeah, what you're saying could be right.
I mean, it would be like it would be like science or like it doesn't really improve the result if you have
No, so we already got what we wanted.
because it's PSD. That's what.
Because from all we know, that's time bound. Because for most reasonable algorithms, we could prove. There are complicated algorithms one can think of for which we are unable to show. Yeah. So this is the statement essentially. So I think if we teach next time, input linear algebra. It's very useful. When I learned it, this was not part of the course. People taught. We teach all other interesting things, but not this. All right.
So